And as you can see over here, we have two triangles within each other. We have the bigger triangle over here, and then we have the slightly smaller triangle within it, and that's this triangle right here. So I know for a fact that those two triangles are similar triangles because they share the same sides. So since we know the length of their bases, that is the length of this triangle right here, we know that the base of it is 0.4 meters, and we know that the base of the bigger triangle, which is this whole triangle right here, is 1 meter. We can use some ratios to figure out what the displacement of point D and point C are going to be relative to one another. So the way this works is that all we have to do is that we're going to take the length of the longer side, which is 1 meter, and we're gonna multiply it by delta C. So that's a delta. Delta is used to represent the displacement of a point. So the displacement of point C is represented by delta. So I'm gonna take the side of the longer triangle with the delta C, and once you multiply those two together, it's the same as saying the length of the smaller triangle, which is that over here, what we have in red, is going to be 0.4 multiplied by delta D. Delta D. So, or if you want, some people like to write it as delta C divided by 0.4 is equal to delta D divided by 1. It's the same thing. So if you want to say this side divided by the length of it, so if you're considering the bigger triangle over here, you're going to say this side of the triangle divided by its own base is the same ratio as the smaller triangle, the side of the smaller triangle divided by its own base, which is 0.4. Either or, those two are the same. So now this is great because we're starting to see some relationship between point C and point D. But let's remember that since we have our moment equation over here, we want something that has FC and FD in it. And frankly, delta C and delta D do have FC and FD within them, because if you look at the equation for delta C, or the displacement of the point, it is given by the force in cable C multiplied by the length of the cable divided by the cross-sectional area multiplied by the elastic modulus. So this equation, this displacement equation, is used when dealing with displacements in cable. So let's say you have a cable in this question, and you want to figure out the displacement of point D after a certain force is applied. All you have to do is use the displacement equation. So you have to figure out what FC is, what the length of the cable is, and some mechanical properties, and as well as geometrical properties of the cable, and then you can easily figure out how far it's going to get displaced by. And delta D rather, is the same thing. So we're going to take the force in the cable multiplied by the length of it divided by the cross-sectional area and the elastic modulus. Now we don't really have to worry about the cross-sectional area and the elastic modulus, although they have given them to us in the question. It's not necessary because you're gonna see that they're actually gonna cancel out later on. So all we're gonna do over here now is we're gonna take this equation, which I'm gonna put a star beside it, and we're gonna plug in delta C into here and delta D into here. So what we're gonna end up with is gonna be 1 meter multiplied by, now delta C is equal to FC. We don't know what FC is. We do know what LC is, and the length of LC is the length of cable C, and it is 700 millimeters. So that is gonna be 0.7 meters divided by AE is equal to 0.4, as we see in the star equation, multiplied by delta D. Now delta D is equal to the force in cable D, which we don't know, multiplied by the length of cable D, which is given by right here, 0.9 meters. Divided by AE. Now, because both cables have the same elastic modulus and they both have the same cross section, then those two are gonna conveniently cancel out. And we are gonna end up with 0.7 FC equals 0.36 FD. And now what we have over here is actually a pretty good equation because it relates FC to FD, so this is perfect for us to use along with our moment equation, which also has FC and FD in it. So we have two equations, two unknowns. If we simultaneously solve for both of those equations together, we can be able to figure out FC and FD. So you can use either your calculator or you can just plug them in by hand. And once you solve for FC and FD, you should get FD will equal to 155,836.25 newtons, and the force in cable C is gonna be equal to 80099.83 newtons. Forget the units. And that basically concludes the first part of the question. So we just figured out the forces in cable, the forces in the first cable, which is connected to point D, and the force in the second cable, which is connected at point C. Now, and that right there is 12 marks, so you just earned 12 marks of that question, which is the greater majority. I don't think there was anything particularly difficult about that part. Now, part B, it says find the corresponding vertical displacement at point A where the load is applied. So this is what they want from that question. Over here at point A, once you apply the 200 kilonewton force, the whole bracket is gonna rotate in that direction. So they want to know if point A started off being over here, then probably after the force is applied is gonna be somewhere over here. Now the trick to doing that part of the question is to utilize the fact that this bracket there's a 90-degree angle over here. We know it's at a right angle, so we can use symmetry in this case to help us figure out the displacement of point A. And the way we do that is, since we know the distance between point A and point B is 0.5 meters, we can likewise create another point right here, and we will call that point A prime. Okay, so the distance between A prime and B is exactly the same as A and B. So if we could figure out what the displacement of A prime is, then that would be exactly the same as figuring out the displacement of this point right here. So what we really need to find out is what the displacement of A prime is. Okay, so that's the idea of doing part B of that question. So as you can see over here, what I've drawn is it's the same triangle that I had in this diagram, except that I've added an extra line over here, which you see in red, and that line is representing the displacement of point A prime. So just like when I created the point A prime a little bit just above point C, this is where the point A prime starts, and this is where it ends up after the force is applied. So if we go back to this diagram over here, this is our bracket, this is after the force has been applied, and all I did was create a point that was slightly above point C. So at the beginning it was here and now it is here. So I just labeled that, as you can see, delta A prime, which is the displacement of point A prime. And the distance is exactly the same as it was before. So like I said, between point A and point B is 0.5, and the distance from here to here is also 0.5 meters, and that's what I did in my similar triangles over here. Now, since I figured out the force in cable D and the force in cable C, I'm actually going to use one of those to help me find out what the displacement of delta A prime is. And I'm going to again use similar triangles, because instead of having now two similar triangles, we actually have three. So we have the one with delta D, the one with delta A prime, and the one with delta C. But we're not gonna worry about delta D for now. We're actually gonna use delta A prime and the delta D triangle. So in order to do that, we're gonna have to first figure out what the displacement of delta C is, and we know that there is a ratio between the displacement of delta C and the displacement of delta A. So if we figure out what delta C is, we can use a ratio between the delta C triangle and the delta A prime triangle to figure out what delta A is. So this is how it works. So I'm gonna actually figure out what delta C is, and delta C is gonna equal to, once again, FC multiplied by the length of cable C divided by the cross-sectional area multiplied by the elastic modulus. Now we've already figured out in the previous part of the question what FC is. So it is 899.83 newtons. Multiplied by the length of cable C, and the length of cable C, if I remember correctly, is 0.7 meters. So that is going to be 0.7 meters divided by the cross-sectional area of the cable. So they told us that the cross-sectional, or the diameter of the cable, is actually 16 millimeters. So using that to get the cross-sectional area, I got it to be 4.02 times 10 to the power of -4 meter squared, multiplied by the elastic modulus of the cable, and they've given that in the question, and it is 200 gigapascals. It says the elastic modulus is 200 gigapascals. So a giga is to the 9, so 200 times 10 to the power of 9 pascals. Now I try to keep my units intact as best as I can, because I know that you can use dimensional analysis anytime during the examination to make sure that the answer you get is correct. So if you actually were to cancel out Newton with meter and meter squared and the units pascals, you would end up with the units meters. So if you actually do go through that as an exercise and you get meters, you know you're using the equation correctly here. So once you crunch all these numbers, you should get delta C to be 6.97 times 10 to the power of -4, which is a pretty small number, as it should be, because although